So here's another problem where we want to find the internal shear force and bending moment at a section C. And just like we talked about before, we want to decide when we cut the structure, do we want to work on the left side or the right side? Now I think in this problem there's going to be a more clear choice. So let me kind of block this off from your view for a second. So when you look at this particular section, you can see the loading is what? It's triangular. And I think you probably all know the area of a triangle and the centroid of a triangle. If you look at the other side, it's a trapezoid. Now, I usually remember the area of a trapezoid, but I don't necessarily remember the centroid off the top of my head. So what a lot of people would do in this case is break it into a rectangular piece and a triangular piece, so you'd have two loads to deal with. So typically, if you have the choice, when I make this cut here about C, try to choose the one that would provide less work. So one triangular load, or on the right-hand side, and I'll sketch this in so maybe you can see it. You can see a rectangular load and an additional triangular load. So there'd be twice as much work to do on this side, twice the forces to keep up with. The left-hand side, one equivalent force to keep up with.
So you can do it either way. Like you can split it and then simplify the distributed loads to point loads, or you can simplify.
We could work it both ways. It's going to give you the same answer.
Okay.
I mean, there's not like, okay, if you do it this side, you'll get an answer, and this side you get a different answer. That's not the case. Let's start with the one on the left first. So when I do that, I'm going to need my reactions. So as you're moving towards the exam, and you're thinking about, saving time and trying to be efficient, this is the sort of thing you want to think about. In this particular problem, it's going to be less work on the left side free body than the right side. Now you can still do this one and be correct, get the right answer, just a little more effort. And if we have time, I may go ahead and demonstrate that. So right now, I think I'm going to work the left side. So doing that, I want to find my reactions at A. So what I want to find here is, to do that, I need to find the total load under this diagram. So it's a triangle, and a triangle is 1/2 base times height. I think that's 1/2 18 times 3, which is 27. And it's going to act at the centroid of a triangle. And the centroid of a triangle is 1/3 the base from the big end. So 1/3 of 18 is 6. So now I'm going to sum moments using right-hand rule about B. Make sure it's in equilibrium. That way I can find my reactions at A, and then I'll work the left-hand side. So about B, this concentrated equivalent force creates what kind of moment? Positive or negative? About B. The 27 kip creates what kind of force about B? A moment about B. Positive or negative? Positive. So 27 kips. And the moment arm from B? 6. Then the other force that creates moment is the reaction at AY. It creates negative moment, and it has a moment arm of 18. So it looks like AY is 9. So now I can sum forces in the Y direction. I'm going to go ahead and do this. Even though I don't need BY for the problem, if I have, I think I might try to work the right-hand side too to show you the difference. So I'll go ahead and get BY while I'm here. So I have AY and BY both acting up, and then 27 acting down. So it looks like By is 18. And then we can sum forces in the x direction, and all I have is AX. So AX is 0. Okay, so let's use our method of sections at C. When I do that, I'm going to look at the left-hand side right now. So I'll draw this a little bit larger. So there's my free body, 6 feet. At A, I know AY is 9 kips. I have a distributed load there. Now the first thing I have to figure out is what is the intensity of my distributed load here. Now I know moving from A to B, you can see that over 18 feet my load goes up 3. So what would be the load at 6? So it's like similar triangles, right? The height of this triangle at 6 feet should be equal to 3 at 18 feet. So what's the height of this triangle? 1. Everybody see that? So 1 is to 6 as 3 is to 18. They're the same. The other way to do it is to establish the slope of the line. What's the slope of the line? Rise over run, so 3 over 18. Right? That's the slope, and then multiply it by 6. And you get the same thing. So that's my intensity of the distributed load at that high end. So what would be my concentrated equivalent force? Well, it's still a triangle. So it's 1/2 base, which is 6, times height, which is 1. So that's just 3 kips, right? And what's the distance from the cut surface to the centroid? Again, it's 1/3 of the distance, and 1/3 of 6 is 2. Any questions about that? So now, at my cut surface at C, I have my axial force at C in the positive direction, my shear at C, positive direction, and here's my positive bending moment at C. And then there's my free body diagram. So for me, working these problems, this is at least half the problem to 2/3 of the problem. If you get this part right, then the rest is just simply apply your statics and you're done. Any kind of thinking, any kind of processing of the information comes in making the cut, deciding which side to use, making sure you get the equivalent amount of force on the object, putting your positive sign conventions down, and at this point, just make sure you're in equilibrium. So using right-hand rule for my sign conventions, I'm going to sum the moments at the cut. Make sure I'm in equilibrium. So with right-hand rule, the internal moment at C is positive or negative? Positive. This 3 kip equivalent force, what kind of moment is it creating about C? Positive or negative? Positive. So the force is 3 kips and the moment arm is 2 feet. And then I slide over to this 9 kip force at reaction at A. What kind of moment is it creating about C? Positive or negative? Negative. So that'll be 9 kips. Its moment arm is 6 feet. So it looks like the moment at C is going to be positive. And it's this is 54 minus 6, 48. Is that right? Anybody out with the calculator?
Yes.
Do you need a calculator to do 54 minus 6?
Yes,
48 kip feet. Positive. Does that make sense that it's a positive bending moment? I say yes, because this beam is probably going to deflect something like this. And you can see that it's pretty much got that positive curvature everywhere. So you'd expect positive moments everywhere in this beam. All right, let's finish up by looking at our shear force. So we just sum forces in the y direction. So starting here on the left side, I've got the shear at C, and it's acting down, so that's going to be negative. And our 3-kip force is acting down. And our 9-kip force is acting up. So it looks like the shear at C is 6. And then last, again, this is a kind of a almost trivial result. When we sum forces in the x direction, all we have is the axial force at C, and it's 0. Any questions about that one? That one took, so far we've used about 11 minutes on this one. Would you like to see, if we'd have chosen the right-hand side, what you'd have to deal with? Or are you guys good with this? Okay, this is the time where you're supposed to make a response. Hey, it's a democracy. Well, they say it's a democracy. So let's vote. All for working the right-hand side, raise your right hand. No votes. Oh, 1 vote. 2 votes. 3 votes. Not a majority yet. Is that 4 votes? Okay, we have 10 of you. We need 2 more. No. Oh, Mr. Apong's hand is forced up by his classmates, so it's a deadlock. I guess I'm ultimately the leader of the Senate, so I can break all deadlocks. I vote yes. So we're going to do it. Why did I put you through that when I was going to do it anyway? I don't know. Just wanted to. All right, so let's look at the right-hand side. We'll start by putting our reaction By on there. Oops, which is, I wrote By, I should have just written 18. Also, this particular length is 12 feet, and it's a trapezoid. I'm going to exaggerate it. We've already talked about the fact that we're going to break this up. Now, we already know from our previous work that the intensity of the load here at 6 feet was 1 kip per foot, so it's exactly the same over here. And we know that this intensity is 3 kips per foot. But what that tells you, that this portion is 1 kip per foot, and that this portion is 2 kips per foot. I have to keep that in mind when we break these things up. I'll go ahead and put some lines here to kind of give you an idea what the forces look like. So let's start with the rectangular one. The concentrated equivalent for it is what? Base times height, which would be 12 kips. And from the cut surface, this distance would be what? Half the length, or 6. The triangular section would be, what would be the intensity of that load? Well, it's going to be 1/2 base times height. So that's also 12 kips. You guys see that? And the distance from the cut to here is what? Now, in our previous work, we were always doing 1/3 from the big end, but it's also then 2/3 from the small end. So 2/3 of 12 is 8. And then at the cut itself, this is one thing I want to make sure that you see. This is positive shear at C, axial force at C. This is positive shear force at C. And this is positive bending moment at C. So you see, if you can compare these two, if I were to take this free body diagram and stick it here and reunite it with the left side, you'd see the shear forces are equal and opposite, so they would cancel out. The axial forces are equal and opposite, they would cancel out. And the bending moments are opposite directions, they would cancel out. So you can see it's a little more complicated free body to keep up with. So there's visually a difference in why the left side is going to be a lot easier to work than the right side. But let's go ahead and finish this. So I'm going to start again by summing moments at the cut. Setting equal to 0. Now, since I'm using right-hand rule for my moments, what kind of moment is this? Positive or negative? Negative. These two forces are going to create what kind of moment about the cut? Positive or negative? Negative. So we'll take the first one here, 12 kips. This is the rectangular load times 6 feet. And then another negative moment created by the triangular piece, which has a concentrated equivalent of 12 and a distance of 8. Then all the way over here is my reaction. That creates what kind of moment about the cut? Positive, and that's 18 kips. And what's the moment arm? 12. So what should the moment at C be equal to? If we're lucky, it's going to be 48. I got 48. Did you guys get 48? Well, that's great. I'm hoping it's 48. You can see they match. Then we'll sum forces in the y direction. Make sure we're in equilibrium. Looking at my free body, I've got a shear force that's acting up. Minus 12 down, minus 12 down. 18 up. So it looks like the shear at C is equal to 6. You can see that matches. And the last one is, again, borderline trivial, but we'll go ahead and check it. We'll sum forces in the x direction, and all we have is minus AC and no other forces, so the axial force is 0, and that checks. A long problem, probably nearly twice as long as it would normally be for you guys, but I wanted you to see to compare and contrast. So when you're working these problems at home on mastering engineering or as you prepare for the exam, make sure that you mentally look at the problem, make the cut, and really look at what you have your choices are, left and right. And try to go ahead and start through the process in your head to see which one is going to present you the fewest challenges. In this case, it would have been the left-hand side. So any other questions before we stop? Okay.